Lesson 4.5 is on proving triangles congruent using ASA and AAS. The ASA postulate says that if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, then the two triangles are congruent. So let's take a look at this picture here. So I have triangle ABC and triangle DEF. If angle A is congruent to angle D, and angle B is congruent to angle E, notice that AB, this side across the bottom here, is the included side between angles A and B, and side DE in this triangle is the included side between angles D and E, and if those included sides are congruent, then I can say that triangle ABC is congruent to triangle DEF. AB and DE are called the included sides because they are between the two pairs of angles that are congruent to each other. So let's take a look at how we would use this in a proof. So we are given that AB is congruent to CD, and the first thing I'm going to do is mark that. AB is congruent to CD. It also says that AB is parallel to CD, and I'm going to mark that. And what I need to prove is that triangle ABE, the triangle on the top, is congruent to triangle CDE, the triangle on the bottom. So of course the first thing I'll do is list my given information. AB is congruent to CD, and AB is parallel to CD. Now whenever I see parallel lines, I think of all of those theorems that we had in the last chapter, where you have parallel lines cut by a transversal, and alternate interiors, alternate exterior, corresponding angles are all congruent, consecutive interiors are supplementary, so I'm wondering if there's any of that going on here. So if I were to look at the line across the top and the line across the bottom as my parallel lines, I actually see two possible transversals. One would be BD going this way, and the other would be AC going that way. So I think what that means is that I can say that angle A is congruent to angle C, and I'm going to go ahead and mark those because if AB and CD are parallel and AC is my transversal, then angles A and C are alternate interior angles. If the lines are parallel, then alternate interior angles are congruent. And actually I think I can say the same thing with angles B and D if I look at segment BD as being my transversal. So I can say that angle B is congruent to angle D. Angle B is congruent to angle D, and that's for the same reason. Those are also alternate interior angles. If lines parallel, then alternate interior angles are congruent. And let's take a look at the picture now. So I have angle A is congruent to C, and B is congruent to D, and it was given that AB is congruent to CD. So I think what I have here is an angle, side angle, angle, side angle. So now I can say that the two triangles are congruent. Triangle ABE is congruent to triangle CDE by angle, side angle. Second theorem here is AAS, and this says if two angles and the non-included side of one triangle are congruent to two angles and the non-included side of another triangle, then the two triangles are congruent. So let's take a look at this picture. So I have angle A is congruent to angle D, and angle B is congruent to angle E, like we did in our last postulate. But in this case, I have a non-included side. Notice that AC is congruent to DF, and that is not the side that's between the angles. In the previous theorem, we had an angle, side, angle, but here we have an angle, and a side. So a non-included side is one of the two sides that is not between the two angles that are congruent to the two angles of the other triangle. And in this case, it's AC, could also be BC and EF if I had those as well. So if two angles and the non-included side of one triangle are congruent to two angles and the non-included side of another triangle, then the two triangles are congruent. Let's take a look at how we would use this in a proof. So given this diagram, I have that angle A is congruent to angle C, and AD is parallel to BC. And I'm going to go ahead and mark that on there. AD is parallel to BC, and I have to prove that segment AB is congruent to segment CD. So the first thing I'll do is go ahead and list my given. And looking at this proof, I'm noticing a couple interesting things. This is different from the previous one because what I have to prove is not that two triangles are congruent to each other, but that two segments are congruent to each other. So I think what I have to do first is prove that probably these two triangles here are congruent to each other, and then I'll use CPCTC to show that their corresponding parts are congruent. So let's see if I can get these two triangles congruent to each other. So if AD and BC are parallel lines, then I'm going to look at BD as being a transversal here. Maybe turn your head sideways and look at it. BC and AD are parallel. BD is my transversal. Then that means that this angle here and this angle here are going to be alternate interior angles. Now remember, I can't just name that angle D and angle B because there's multiple angles that have D and B as their vertices. So let's name this one angle CBD. That's the one at the top. Angle CBD, oops, is congruent to angle ADB. And that's because if the lines are parallel, alternate interior angles are congruent. Okay, so now I have two angles of the triangle on the left are congruent to two angles of the triangle on the right. What I really need is another side. And what I'm noticing is that BD is congruent to itself. So segment BD is congruent to segment BD. And that's by the reflexive property. And I'm going to go ahead and mark that on there. Just put a little mark right there. So now I have two angles and a non-included side of the triangle on the left are congruent to two angles and the non-included side of the triangle on the right. So I can now say that triangle CBD, that's the one on the right, is congruent to triangle ADB, and actually the order doesn't matter. I could have said ADB, oops, is congruent to CBD, and that's by angle, angle, side. Now that these two triangles are congruent to each other, I can say that all of their corresponding parts are congruent. And what I'm trying to prove is that AB across the top is congruent to CD across the bottom, and indeed I can say that because corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent, or CPCTC.